Hello, and here's a little summary of some of the programs we didn't get to do. I'm not going to explain all the code on this one, just going to show you some of the stuff we could have done based on what we know. Let's see, what if I show you my repository for this code? La 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 la. Okay, which would be in pastebin. Alright, and the first thing I'd show you, I guess, would be, oh, where is it? Rational. Here's a rational class. It takes an integer over an integer, makes a rational number, a fraction out of it, and it has a toString, and it has multiplying rationals and adding rationals and reciprocating rationals and getting common denominators and dividing rationals, all kinds of fun things. Look at the tester part. Okay, here it is. Construct a rational 1/2, another one 1/3. Let's add them up, print them out. How about 8/9 and 1/9? And let's add them up and print it out. And 4/17 and 7/3 and multiply them and print it out. And that's the answer there. And more multiplying. Okay, so let's test this out. Let's see, where would I put this? Okay, I have it in here. Do I not? Where do I have it? I think I have it in here, actually. That's where I have it. Do I not? There it is. There it is. Oh, I compiled it already. All right, well, let me just Java C it and everything else. So Java C, rational, no. Rational.java. There you go. Not so. Oh, cd this. It's in a subfolder. There it goes. Okay. And then Java it. And there you go. So that was adding and adding and multiplying, and I don't know what that last one was. What was that last thing? I had it in here. What was it? 0, 6 is 0. Okay, constructing 0. Okay. So there was the adding, and there was the adding, there was the multiplying, there was the multiplying. Okay, fine. But what if your integers get really, really big? Your integer numerator and integer denominator. Well, then we have the following. Is it here? No. Where is it? I have something called the big rational. There you go. And in big rational, we use the big integer class, which actually uses a static array of ints to represent enormously long integers as an array of integers, array of digits, in other words. And so it does all the same stuff. It constructs a big rational number. You can toString it. You can times multiply them. You can add them. You can get reciprocals and divide them. Let's see what the tester do. The tester is trying to approximate E, if I recall. Is that what we did? Yeah, we did factorial. Apparently we have a factorial method in here somewhere. Factorial equals factorial times big rat. Well, it's just multiplying. It's making factorials and then adding up the factorials, and that eventually gives you E. So let's compile that. I'm going to Java C big rational. There you go. And then Java it. Oh, and I think the number of terms, 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial comes from the power series for e to the x. If you plug in 1, you get that series. So if you do one term, you get, well, it said, probably starts at 0. Doesn't give you anything, does it? Okay. All right, 1 gives you the sum of the first two terms. Then 2, then 3, then 4, then 5, then 6, then 7. Let's see, we're going to break maxint. Maxint is like 2 billion something. We're nowhere near maxint yet. 8, and now it's not giving you a decimal, which would be nice, but it's giving you a big rational over a big rational. So it's doing all the adding and multiplying and combining and using common denominators get simplest form fractions. All that fun stuff. So this is working. Let's see, 10 and how about we jump to 15? There you go. Now that's, how big is that? Let's see, millions, billions. Yeah, this is 888 trillion something over 326 trillion something, which is darn close to E, but the integer, the denominator and the numerator are way over max int. Let's see, can we do 20? Can we do 30? Wow. Can we do 40? And it gets hard to read, but there you go. Okay, that's the idea. After that, let's go back to some graphics. Here's another nice polar graph. Let's see. If we go over here, I can show it to you. Let's see, what was it? I think it was butterfly. Butterfly is, again, doing r times cosine theta and r times sine theta for the x and y components. And this is the polar function, which is completely insane, but let's see what it looks like. Let's go back here and Java C butterfly. There you go. And just run it. It's like our rows program, but another strange design. There you go. Very nice. And it sort of iterates over itself and gets a little more intricate. But that's the design right there, sort of like a butterfly. Sort of reminds me of the Lorentz attractor in 3D, but this would be like a 2D projection, I guess. Okay, and there you go. Very nice. Oh, you get the idea. There you go. All right, so just going to repeat a lot of those. It's going to get more and more intricate, but the same design over and over, pretty much, with a slightly larger or smaller radius from the pole. And does it have polar axis symmetry? I guess. Yeah, it does. All right, let's finish that. Alrighty, what's next? Here's a graph called Madness. Whoops, not here. Where is it? Let's take a look at the code for Madness. This is code I wanted to do in class. We ran out of time. Here's Madness. Madness is not polar in that you have r times cosine and r times sine. It's parametric. You have x is a function of t and y is a function of t, and it's not really polar. But look at what it does. Let's see. All right, let's just run this. So let's go over here. So Java C Madness. There it goes. And I don't think it needs any args input, any command line input. So let's run it like this. And you get some really crazy design. And then it starts to repeat more or less. Make it a little more intricate. And there you go. It's a little bit, a little bit of a shift there. Horizontal shift, I guess. And just keeps on going and going and going. Isn't that nice? Very interesting. La la la. There you go. And so very nice. Nice and smooth curve there. And there we go, and there we go, and there we go. And there we go, and there we go, and there we go. Alright, so I think that's pretty much, that gives you the idea of what's going on. Okay, let's leave it at that. And here's a real dragon curve. Now, the real dragon curve is mutually recursive code. We haven't talked about that. It's very odd. Here, take a look at this. Where is my dragon? There it is. So, if you go to main, right? Here's your main. It does a loop. No, it doesn't do a loop. It takes args input, n equals 0 to 14, I guess. And this should say 0 here. And then it calls this static function called dragon. All right, so what does dragon do? Dragon picks one of these dragons to draw, depending on which number. This is sub 0, sub 1, sub 2, sub 3, 4, 5, 6, I guess to 14. And then it uses turtle graphics to graph something, but look at what it does. It calls dragon, which in turn, it calls itself, and then it calls no guard, which is dragon backwards, which is this guy, which does the same kind of calls but reversed. And as a result, you get these crazy dragon curves. Let's take a look at it. I don't want to get into the theory here right now. Java C is just an overview. Dragon, dragon. And then Java it, and then let's say, I think you can pick 0 through 14, so let's put in 0. And it's just a line, okay. But look at what happens if you do dragon level 1. You got 2 lines. And then dragon level 2. Alright, so it goes forward, turn left, forward, turn left, forward, turn left, forward, turn left, forward, turn right, forward. That's what it's doing. Okay. Here's level 3. Okay. So forward, turn left, forward, turn left, forward, turn left, forward, turn right, forward, turn left, forward, turn left, forward, turn right, forward, turn right. See how it's going? Okay. And then you get more and more intricate designs. There you go. And I think it can go up to 14. It said 1 to 15, but I think it was 0 to 14. And there you go. Very nice. And it gets smaller and smaller in our scale. Our scale isn't changing. I think it's 0 to 1 for X-min, X-max, 0 to 1 for Y-min, Y-max. And these are nice dragon curves. There you go. Very nice. So these are space-filling fractals, as I call them. Alrighty. Filling in a 2-dimensional space with a fractional dimension between 1 and 2. And there you go. Alright, can I put in 15? Let's jump to 15. Is 15 allowed? It is, okay. So I think it should have said 0 through 15, not 1 through 15. And that's getting more like a dragon. There you go. There's your dragon standing up, rearing its ugly head and wings and things, I guess. That's why it's called a dragon. Alrighty. Well, that's going to take forever, so let it go for a second, and then we'll have to move on. Go ahead, go ahead. Alright, we get the idea. Alright, so goodbye. Bing. Alright, what else? Did you see Rise of the Planet of the Apes, the latest version of Planet of the Apes, where the ape actually learned how to do the Tower of Hanoi problem? Wow, take a look at this. This is another recursion. Where's my Hanoi? This is an animated version of Hanoi. Alright, there's your code. It's recursive, and what it is you have a certain number of pegs, say 3, and a certain number of disks of different sizes, like, let's say, I don't know, 4. And you stack them, the largest on the bottom, smallest on the top, in decreasing order of radius. And the idea is, can you move all of them, all of those disks, to another peg by moving one disk at a time, from one peg to another, and never allowing for a large disk to be on top of a small disk. Okay? So let's see this animation here. Now wait, where's the tester? Does it take args? The number of disks. Alright, so I think this is set for 3 poles, and you can tell it how many disks you want. Okay, so let's try that. Whoops. How about with Java C animated? Where is it? Java C animated Hanoi, I think it's called. Oh wait, I don't think it's here. Hang on. Where is it? It's in its own directory here. Where? Hanoi. Okay, so CD Hanoi. There you go. There it is. Dang it. Okay, so Java C animated Hanoi. There you go. And then run it. You know, if we had more time in class, I could explain how all this stuff works. Maybe next year we'll get to do it. Oh wait, I have to tell it how many disks. So, can you put 0? Yeah, it doesn't do much. Okay. Can you put 1? There you go. That was easy. One step. Okay. Can you do 2? You didn't see the original setup. The original setup was these 2 discs over here. And I think what it did was it moved the blue one, it moved the red one, and then it removed the blue one. Okay. It'll take longer as you put on more discs, so you should be able to see most of the animation eventually. There you go. There you go. There you go. There you go. Boom. And I think the ape in, and even outputs what it does. See, isn't that nice? The ape in the Rise of the Planet of the Apes, from I think 2010, last summer, actually did this with 3 pegs and 5, which is considered very difficult to do by hand. With 5 discs, this is 4, so this is 3/4. There you go. Now it's getting crazy. How complicated it gets. Okay, let's do the 5. And here's 5. Okay, boom, 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 boom. So the recursive algorithm built into this program actually handles getting all the pegs from one side to the other without ever moving one disk at a time without having a large disk over a small disk ever. And I don't know, this gets crazy. How about 10? This could take a while. Yeah, this might take forever, actually. I might have to stop this. But now you see the algorithm. Yeah, you keep on alternating the top of the original pyramid to different stacks, making it bigger and bigger as you go. Alrighty. Well, actually, we're almost there, aren't we? Alright, because we've dealt with everything but the bottom 3. Everything except the bottom 3. Wow, this is taking a while. Okay, come on. It's almost done with everything but the bottom 3. Come on, you can do it. Oh, wow. Yeah, it's really going to get slow after this, so once it's done with this stack. There you go. Well, it was done with that stack in the middle, and now we're trying to put it over here. Okay, I think we're done. This is going to take forever. Okay, bye-bye. And how about this? Iterated function or systems, or iterated fractals. Let's see, where do I have that in here? IFS, yes. Okay. All right, let's take a look at that code. I have it here, but I also have it here, so. All right, so this is my paste bin. Right, you can look at all my code up here. This is all the code we've done all this year in computer science, all this stuff. All the way back to chapter 4, even before that. All the way back to Hello World in chapter 1, 2, and all of this stuff is here. Okay, let's get back to IFS. And here you go. And so you can input different parameters. This uses like input files. Remember Chess 960 we had an output file? This has input files. And it uses a standard in class that they made up instead of easy reader. I guess I could write this with easy reader. And it does all this crazy calculations here. All right, so you could do some nice stuff here. Like, let's see, let's try this. Let's go here. Let's Java C IFS. There you go. And then what input files do we have? Tree, Coral. Okay. So I think when you run it, you have to say how many iterations you want. Let's say 100, and which file to read from. How about Coral.txt? Let's get rid of the C in Java C and see what you get. And this gives you a little design that looks like a coral reef, except you need more iterations. Let's try 1,000. There you go. It gets more and more interesting as you iterate. How about 10,000? You can look up all this stuff on Wikipedia, Sierpinski triangles, Koch snowflakes, iterated function systems, dragon curves, fun stuff. Let's see, is 100,000 going to take forever? Let's see. Let's see. I guess it's almost done. I guess it's done. Is that it? That's it. Okay, let's try a different input file. How about Barnsley? What's that? Wait, hang on. Barnsley. There you go. Let's see what this does. Oh, it's like a fern. A leaf from a fern tree or something. All right, how about Sierpinski? So this gives you like a Sierpinski triangle, fractal. All right, and tree. And there you go. That's nice. All right, I think my favorite was the Barnsley, the fern. It's almost like a tree. There you go. That's my favorite. There you go. So that's it. Next recording, I guess tomorrow, I'll do a little bit with Mandelbrot fractals. And this one we'll explain from the ground up. We need to construct complex numbers, make our own complex number class, do a little arithmetic and stuff. All right, so enjoy. Hope you had fun with our little escapade here. And let's get rid of this. And let's get rid of that. And that. And bye-bye, YouTube. No? Okay. We'll say bye-bye this way. Almost there. See ya.